12,
11,
10, 9,
8, 7, 6, 5, 4, 3, 2, 1.
Good evening and welcome to the wonderful world of chemistry, a magic show. I'm Neil Hazari. I'm from Australia. That's why I sound funny. And it is our pleasure to captivate you tonight with a series of chemistry demonstrations and also to explain some basic concepts of the discipline that we love to you. Now, this show comes with a warning. What you see tonight should not be repeated at home. The people doing these demonstrations are trained experts. They have spent years practicing for tonight. So who are these people? Where have they come from? If we're going to introduce the team, we of course need some music. So first, from Massachusetts, he loves lawn games. He loves the Patriots. He is David Charbonneau. From New Jersey, she loves colors. She loves running. She loves to talk. Julia Curley. From Toledo, he plays the mellophone. On his birthday, he likes to read a book by himself. Nicholas Smith. From Florida, she loves her pet bunny more than anything else in the world, Emily Bath. Also from Florida, he's fluent in Spanish. His pet cat loves to play with Emily's pet bunny, Matthew Espinoza. And finally, ladies and gentlemen, we have a star with us tonight. A person who has captivated thousands of Yale undergrads with his demonstrations. You see, chemists are not very famous, which is a shame. But if this man was a basketball player, he would be LeBron James. If he was a movie star, he would be Bradley Cooper. Would you please welcome the one and only Professor Patrick L. Holland. Okay, so you are here today to learn about chemistry. So first, we have to tell you what chemistry is. So chemistry investigates the composition, properties, and behavior of matter. So of all of those words, matter might be one that you are not familiar with. What is matter? Matter is anything that occupies space and has mass. Look around you, touch things. Pretty much everything you can see and feel meets that definition. Dave is matter. The walls are matter. The chairs are matter. And what is this matter made of? So it's made of very small particles which are known as atoms. Atoms are so small that you can't see them. Now, if we think about how we construct words from letters. Now, we construct matter using atoms, but we have a lot of different atoms to play with. In fact, we have 118 different atoms which are known as the elements. And these elements have different properties because they have a different number of protons, neutrons, and electrons. Now, to do our first demonstration, where we see the different properties of the elements. Please welcome Professor Holland.
Excellent. Welcome, everyone. And I am going to show you one of the ways that chemists have of getting different elements to reveal themselves. Oh, do you need to? Oh, let's help. Safety is the most important thing in chemistry, and so we need. Yeah, you okay?
Yeah, I just sprinted a second.
Okay. All right. Great. All right. So we're going to look at one of the ways that chemists get elements to reveal themselves, and we can tell what different elements are. And that's because if you heat them up to a high temperature, different elements produce different colors. And if we want to make them go to a high temperature and produce those colors, how might we go about that? Yes, so we have a very good way of doing that here. And what I'm going to do is I have these samples of different elements, and you can make a guess at what color it's going to turn. But in order to do this effectively, we need to have some mood music and some mood lighting.
Good enough?
All right. So this one is strontium. See if you can guess what color this is going to be, or whether my lighter is going to work. Okay, ready? So that makes a red color. This one has sodium. What color do you think it might make? Oh, let's see. Let's see. That one makes orange. And here I have potassium. What color? Oh, I heard a purple. That's pretty close. How about this? Now, this is actually what people use in fireworks. So these are some of the vibrant colors that we get in fireworks. For example, lithium makes a really awesome color that you've seen in fireworks before. This one is barium. It makes a different color that you see in fireworks. And finally, copper makes a different color. I think I heard it. So the next time you go see some fireworks, this is the way it works, is that there are different elements in there. Okay? Great. Thank you.
So elements have different properties, and we know that chemistry is the study of matter. Why is it important to study chemistry? Let's have a look at where chemistry is. It's in pharmaceuticals. If you have solar panels on your roof, chemistry is responsible for the fundamental principles of those solar panels. If you're like me and you play with a rubber ducky in the bath, that's only possible because of chemistry. Paints, cosmetics, plastics, your iPhones, all of the things that we use on an everyday basis are derived from chemistry. But I want to give you one more reason why chemistry is important. Does anyone in here like movies? Almost everyone. And when you're watching movies, one of the things we like are special effects. And chemistry is responsible for some of the special effects in the movies. Let's have a look at this. So here we have a man on fire. You might be interested in how the chemistry of this works. Let's introduce Dave to give you an explanation about this.
All right, thank you, Nile, for demonstrating to us all that chemistry is indeed everywhere in our daily lives. And it's my privilege today to be able to show you guys how Hollywood producers use chemistry for their special effects to make it appear as though one of their actors was on fire. So their actor just appeared to be on fire. That was not done in one take, and the actor was not disposed of. So I asked several of my lab mates if they would volunteer to help me with this demonstration. And not so shockingly, they all said they did not trust me to set them on fire. A smart move on their part, perhaps. But I am so confident that what I'm about to do will work that I'm willing to put my own money on the line, literally. So I will put my own money out and set it on fire. Neil, I forgot the money.
Should I trust him? What do you think? Who thinks they should trust him with a $1 bill?
How about 10?
Who thinks they should trust him with a $20 bill? $20 bill it is.
All right. So I am so confident that this will work that I will set someone else's money on fire. Need a beaker. So what I have in front of me is two solutions, one of which is ethanol. Ethanol is a flammable liquid. If you expose it to a flame, it will set on fire. I also have a graduated cylinder of water. As we all know, water will put out a flame, and if you expose it to a flame, it will not ignite like ethanol will. So, if I'm able to combine water and ethanol in the right proportions, and let's see how steady my hand is here. Great. I can then soak this dollar bill in the water ethanol mixture.
Dave, it's a $20 bill, and it's mine?
Not a problem. So I can then soak this $20 bill in this water ethanol mixture, and I can ask my assistant, Matt Espinosa, to come over here and light this on fire. I'd like to point out that since I'm not the one lighting it on fire, I have no responsibility if we burn this $20 bill. All right, here goes nothing. Neil, I burned your money. But just a little.
Thank you, Dave. Okay, so we just learnt about the elements with Professor Holland. And the elements are the building blocks. It's like if we want to make if we want to make words, we use letters. In chemistry, we might want to make molecules. And to make molecules, we link different atoms or elements. So what's an example about this? One molecule that's in the news a lot at the moment is carbon dioxide. Carbon dioxide has one carbon atom and two oxygen atoms. Water has one oxygen atom and two hydrogen atoms. Methane, which you will see later in the show, has 4 hydrogen atoms and 1 carbon atoms. Now we know with words we can have simple words and we can have more complex words. These are all examples of simple molecules. Let's have a look at the structure of some more complicated molecules. On the left, we have caffeine. Kids, this is what makes your parents get through the day. And in caffeine, we have a carbon atom, lots of carbon atoms, some nitrogen atoms, some oxygen atoms. And then on the right, we have penicillin. Penicillin is an antibiotic. If you're unfortunate enough to get a bacterial infection, you might be treated with penicillin. And this has a sulfur atom, so many hydrogen atoms and carbon atoms. And the links between different atoms are known as bonds. So carbon dioxide has a bond between a carbon atom and an oxygen atom. Now, let me ask you a question. Does anyone know what this molecule is? All right, someone has their hand up here. Ascorbic acid. That is a good guess. But ascorbic acid has a little bit of a simpler structure. Any other guesses? Pardon? Glucose. That is a very good guess. So one of the components of this molecule is glucose. The other component is fructose, and that gives us sucrose or sugar, which we all know and love. And so sugar is in candy. I wasn't quite sure who told me glucose, but here is some candy. And just like different elements have different properties, different molecules have different properties. And to show you that, Emily is going to do a demonstration.
Thank you, Nile. So ions are atoms or groups of atoms that have a charge. So in these 3 test tubes in front of me, I have a solution that's made of ions, and I'm going to drop in some metal salts that are also made of ions. And when I do that, the ions in the solution and the ions in the metal salts are going to change places. And we'll see some magic happen. So this experiment is called a chemical garden because you can see it grow like a plant. So some of you might have gardens at home or be familiar with gardening, but you've maybe never seen a chemical garden before.
So guys, if you look at the first chemical garden that Emily prepared, you can see it's really starting to sprout. And if we be patient, we're going to see the other one sprout. But before we do that, does anyone in this room remember that I gave Dave a $20 bill? What happened to that $20 bill? I never got it back.
I'll write you an IOU.
Where's the bill, Dave? He burnt it.
Only a little.
Emily, how's our garden going?
It looks like it's growing great to me.
Looks like it's going great to you. So what we're going to do is at the end of this show, we're going to check back in on this garden and have a look at how much it's grown. Okay, so right now, especially earlier this week, it was really, really cold outside. And when it was cold, all of the water had turned to ice. And what we have is different atoms or different molecules have different phases. So when we have water in the form of ice, it's a solid. When we warm up water, it becomes a liquid. And it's even possible to convert liquid water into a gas if we heat it up further. So if you go past a factory, you see steam, which is gaseous water being emitted from the towers. Now it turns out that all different elements and molecules can exist in these three phases. And to show us something much more dramatic, we're going to see Dave, who owes me $20, come back.
Hi, I'm the one that burned Nilay's money before. So, as Nilay mentioned, different materials can exist in different states of matter. And today, I'm going to show you guys sort of an atypical demonstration of different states of matter. So when I say nitrogen, typically you'll think of a gas. This gas composes 75% of our atmosphere. However, if you cool nitrogen down to a low enough temperature, you can actually get nitrogen to be a liquid. Now you'll see this smoking a bit. This nitrogen is very cold. Does anyone know what temperature water freezes at? Someone just shout it out. Let's hear it. 32. Yeah, 32. 32. You guys got it. 32 degrees Fahrenheit. Now, can anyone guess what temperature this liquid nitrogen is that Julia just poured? Let's hear someone. Yell it out. 100. Lower. Negative 300 degrees Fahrenheit. Yeah. So, we also know the temperature of boiling water, right? Someone yell it out for me. In Fahrenheit, what is it? 212 degrees Fahrenheit. So that makes a difference of about 500 degrees Fahrenheit between these two materials, boiling water and liquid nitrogen. If I were to add nearly boiling water to this liquid nitrogen, what would happen is the nitrogen would rapidly warm up and become a gas. And so I'm going to do that demonstration for you guys. But first, you may notice that these seats are empty. This is the reason. Sorry, this is a reason. Better now. Julia, may I please have the hot water? So you can see it's steaming. Just pour it all. Yeah, just keep going. All right. All right, someone give me a countdown. 3, 2, 1. Yeah, I'm gonna just get this kind of out of here. No, it's a lot of water though, so it'll melt. Yeah. Kurt, would you mind just making?
What do you think? What do you think, guys? Should I let Dave keep my $20 after that? All right. So we've talked about matter, okay? And it turns out that all matter has mass, all atoms have mass, and all elements have mass. So let me ask you a question. What weighs more, one feather or one brick? One brick. Okay. And just like this kind of matter has different mass, atoms and elements have different masses. Okay, so why does one feather weigh less than one brick? It's because of density. And density is the mass per unit volume. So the brick is very heavy in a very small volume, while the feather is very light in a large volume. Let me ask you a question. Do people think that gases have density? Yes or no? So we're scientists, so we don't like to take anyone's word for things. We want to do experiments and demonstrations. So please welcome back Professor Holland and Matt to show you whether gases have density.
Excellent. Can we get the lights back up on us? Thank you. All right, so like you just heard from Professor Hazari, we like to have experimental tests of whether these gases have different densities. And we have a couple of different gases here, and we can test this in two different ways. One of them is to see whether the same volume of this gas weighs more than air or less than air. And we can do that by, say, taking some of it and seeing whether it floats or not. So this one, mine looks like it floats. What do you think this gas might be? Helium, that's right. It could have been. It's helium.
Well, I actually got a different gas. I wonder if mine will float. What does everyone think? I think I picked the wrong gas.
So Matt's gas is heavier than air. So that's one way that we can test it. But there's a more fun way that we can test it as well, which is because different densities of gases make the speed of sound different. And so that influences the pitch of what we hear. And you might have seen this with helium. Maybe we can share a little bit of, okay. We can try out a little bit of helium and see what it does to the pitch of our voices.
Hello? Hello, Frank.
What do you think, Matt?
I think it works.
I think it works. Nile sounds like this all the time. We have to breathe helium to do it. All right.
So this other gas that is, oh well, okay, this is so fun. And we still have a balloon left.
You never know what might happen.
So, we have a second gas here. Whoa, my voice isn't quite back yet.
So what do you think's going to happen with a gas that's heavier than air? Oh, let's find out.
Well, it has a really interesting influence. What do you think, Matt?
Unlimited cosmic power.
This happens when you're ready to be a real chemist. It's pretty good, don't you think?
Yeah.
All right. All right, that's our show.
Now, guys, please remember, you cannot do this at home. No inhaling of helium, no inhaling of SS6. So far, what we've seen are perhaps the least exciting parts of chemistry. To me, the most exciting part of chemistry is when chemical reactions occur. This is when you take two substances, we can call them A and B, and they might form new substances, which we can call C and D. So some of us, when we go out in the sun, our skin burns. That is a chemical reaction. Let's have a look at a generic chemical reaction written out in terms of the molecules involved. Here we have one molecule of hydrogen. There are two hydrogen atoms here, reacting with half an equivalent of oxygen, which has two oxygen atoms in it, to make water, which has two hydrogen atoms and one water molecule. And this might be important in cars of the future, which instead of operating off gasoline, will operate off hydrogen gas. When we cook, we are doing a chemical reaction. Chemical reactions are crucial to our everyday existence. Now, one other reason that chemical reactions are extremely exciting is because they're often very good to look at. Let's welcome Emily back to show us a very distinct chemical reaction.
Thank you, Nilay. So when we do a chemical reaction, because atoms and molecules are so tiny, we can't always observe directly what's going on and what molecules we have in solution. So one way that we can do that is by using something called an indicator, which usually changes color when a certain compound is present. So in the beaker up here, I have a source of iodine, and starch is an indicator for iodine. So if I add in a starch compound, nothing happens. But the magic happens when we add a solution of hydrogen peroxide. So this reaction is called an oscillating reaction because it will keep changing color like this on its own for about 5 minutes.
Okay, so you can keep looking at this reaction while I'm talking, but chemical reactions are very important in energy systems, and energy is obviously crucial. Okay, to get here, most of you would have taken a car. We needed gasoline to fuel the car. Right now we need to heat our homes. That requires energy. And the main forms of energy that we as a society use at the moment are oil, natural gas, and coal. All of these, when we burn them, release CO2, or carbon dioxide, which we know is deleterious for the environment. What we would like to do as we move forward is use more renewable forms of energy, such as wind, biofuels, or solar energy, which will have less bad consequences for the environment. But let's talk a little bit more about how we generate energy from either oil, natural gas, or coal, or these renewable sources. So when we're burning oil, methane, natural gas, what we're doing is we're doing a combustion reaction, which you all know better as fire. And when you stand next to the fire at a campsite, you get heat released and it warms you up. So here is the chemical equation for when you burn methane. And methane is the primary component of natural gas, which most of you will use to power or heat your homes. So we have one molecule of methane. So you have a carbon with 4 hydrogen atoms. 2 molecules of oxygen react to make carbon dioxide, which is bad for the environment, and 2 molecules of water. Why is energy released when you do this combustion reaction? It's because the bonds, remember the bonds are the links between the atoms, contain more energy in the molecules on the left-hand side of the slide than the molecules that are on the right-hand side of this slide. As a consequence, we release energy when we do this reaction. Now, does anyone want to see us do a combustion reaction? Yes. Let's welcome back Professor Holland and Matt to show us their favorite combustion reaction.
I promise I won't burn any more money. So as Professor has already mentioned, combustion reactions release a lot of energy in the form of heat. So what we're going to be doing for this demonstration is capturing methane in bubbles, and I'm going to place them in my hand and light them on fire. So this is going to release a lot of heat, and I prefer to keep my hands and keep them not burnt. So does anyone have any ideas on how I can protect my hands? Gloves are a good suggestion. Any others? Anybody but Dave? Yeah, just call it out. Fake hands, yeah, I wish I had those. I don't, though. Water, I hear water in the background. Right. So water.
Who said water? We'll give you some chocolate.
And we have some water.
So water is very good at capturing heat. And so I'm going to go ahead and grab some of these bubbles.
All right.
Does anyone think we can get bigger? Yeah. I agree. Go big or go home. I got this. Here we go. Thank you very much, everyone.
So, heat is one form of energy. Another form of energy is light. And we are all exposed to light energy through the sun, right? It heats us up. It keeps us warm. Now, just like some chemical reactions can release heat, some chemical reactions release energy in the form of visible light. And I told you earlier that one of Julia's favorite things was colors. We're going to welcome her back to show us a demonstration which releases a lot of light energy.
Thanks, Nilay. All right, so like Nilay said, I absolutely love colors, and I especially like bright colors. So I'm going to talk today about a compound called luminol, and luminol has a property called chemiluminescence. Chemiluminescence sounds like a fancy word, but all it really means is that when you mix it with the right chemicals, it produces a nice glow. And this demonstration would work a lot better with some mood lighting, please. Great, thank you. All right, so I have 2 flasks, one in each of my hands, and I'm going to pour them down this spiral tube. And as you can see, as soon as the 2 liquids mix, they start to glow. This process is the same thing that makes glow sticks glow, if you've ever used them on the 4th of July or at parties. And it's the same thing that makes some type of jellyfish glow in the water as well. And it's one of my favorite reactions.
Julia, what if I left my blood everywhere? What would happen?
You would probably want to go to the hospital, Nilay. But if you've ever watched a crime scene TV show, luminol can be used to find blood at different crime scenes, and when it reacts with the blood, it actually glows. So if you've ever seen on TV people trying to track somebody using their blood, that's using luminol.
Okay, so when we have energy in the form of light or energy in the form of heat, it's very easy for us to touch it, to see it, to feel it. But not all forms of energy are so easy to detect. So when we have radioactive materials, it's often hard to tell if a material is radioactive. Now, fortunately, we need a certain amount of radiation in order for a material to be dangerous. Nevertheless, we need a way to measure how much radiation an object is producing. And to show us how we measure the amount of radiation that is released, please welcome back Professor Holland.
Thanks. Can you put the lights back up there, please? Excellent. So yes, like Professor Hazari said, this is one more example of how chemists do measurements so that we can understand what's going on. And the way that we measure radioactivity is using this. Does anyone know what it's called? Yeah, it's a Geiger counter, exactly.
Who said Geiger counter?
Oh, excellent, good work. So what's interesting about radioactivity is there's a little bit all the time. There's some coming from the sun, there's some coming from some pretty common materials that are around us all the time, and some that you might not guess. For example, natural potassium has a little bit of radioactivity. And so, let's see, we have here, it's called no salt. It's people who have high blood pressure and need to cut down on their amount of sodium. They can use potassium chloride instead. So it's a salt replacement. You can buy this at the store. And if we pour some of it in this, you can hear yourself whether there's any radioactivity. So you can buy radioactive things at the store, believe it or not, but not very radioactive, luckily. We all know that bananas are rich in potassium. What do you think? No. We know that bananas are rich in potassium relative to other foods, but they're not completely made of potassium. So your banana's not very radioactive. Now there are other things around that you take for granted. For example, your silverware and the bowls that you use. Bowls are made of clay, and they have a tiny bit, which you can detect a little bit there. But they used to use glazing on certain bowls to make them nice and brightly colored that had uranium in it. And so this is in the 1930s that you could buy bowls like these. And we have some that are, well, maybe not the best thing to be using at home. Okay? So I hope that I've sort of let you know that this is one of the things that as we learn more over time from chemistry and we learn how to detect things, we learn how to make ourselves safer and, and eliminate products that are bad for us. Okay? All right. That's what I wanted to tell you about.
Okay, so we've seen a number of examples of chemical reactions so far tonight. When we're starting a chemical reaction, it almost always requires some kind of input of energy. There are a variety of ways that we can put in this energy. Does anyone know what the most common way is? Here. Heating, that's right. So, when we're cooking, we're doing chemical reactions, right? That's why our egg changes when we put it on the stove. And what is driving or starting that chemical reaction is heat. There are other chemical reactions, which Julia in particular likes, which are initiated by light. And in that case, we have energy being put in the form of light. Now Nick is going to show us a chemical reaction which starts with heat, but it's a special chemical reaction, which I'm going to let him tell us about.
Hi there, everybody. So I have here a block of dry ice. In fact, a couple of blocks of dry ice. And what I've done is inside of the dry ice, I have placed a little bit of magnesium. Magnesium is a metal which is a little special in that it burns at over 4,000 degrees Fahrenheit. So what we're going to do is we're going to react it with the dry ice. Dry ice is carbon dioxide that's been cooled down and is a solid. So I'm going to turn on this ventilation here. Sorry about that. The problem is that as the carbon dioxide cools down the metal, it very quickly evaporates and turns back into a gas, and then it makes that sound. So what I'm going to do here is provide a little bit of input energy to this reaction using this, a blowtorch, and we will see what happens. And there you have it. The magnesium has reacted with the carbon dioxide and has formed carbon as well as magnesium oxide.
Okay, so we can start chemical reactions with heat, but sometimes we don't want to have to put in a large amount of heat to start a reaction. Heat takes energy. Where do we get that heat from? It's not always possible. So what we can do is we can find what is known as a catalyst. And a catalyst can lower the amount of energy it takes to start a reaction. So how does it work? A catalyst is essentially a substance that will change the rate of reaction without being consumed in the reaction. So that's even more cool. We put it in, it does the chemical reaction, and we get it back at the end of the reaction. Now, does anyone in this room have a water bottle with them? Yes, okay. So I don't think that's a plastic water bottle though, correct? Yes, it is a plastic water bottle. Okay, so that plastic water bottle was almost certainly made using a catalyst. And the catalyst that was used to make that water bottle was probably a zirconium complex. And the zirconium complex is such an efficient catalyst that if we have 1 gram of the zirconium catalyst, we will make 1,000,000 grams of the plastic. And the catalyst is so good that we don't even remove the zirconium from the plastic, because that level of zirconium in that amount of plastic doesn't cause a hazard to anyone. So what we have is we have a slow reaction or no reaction, where we have 2 molecules, A plus B. They look at each other. They don't do anything. They won't go to C or D. It might take 500 years, 1,000,000 years for that process to happen. We add a catalyst and we get a fast reaction, sometimes instantaneous at room temperature. 90% of commercial products that are available are made using catalysts. So these things that we had on our earlier slides, pharmaceuticals, detergents, cosmetics, are all made using catalysts. Now I think we're going to welcome back Nick and Julia, who are going to do a demonstration which illustrates what a catalyst can do.
All right, thank you, Nile. So now that Nile has introduced you to what a catalyst is, we're going to show you a little bit of a demonstration. So have any of you ever thought to yourself, how does an elephant brush his teeth? You use toothpaste. Well, an elephant would obviously need a very large amount of toothpaste. So what we have here is 4 flasks. Each of them have some hydrogen peroxide in them. And what happens when hydrogen peroxide, a very unstable chemical, falls apart is it produces a lot of oxygen gas and water vapor. Now, that happens by itself rather slowly. So what we're going to do is we're going to add in a catalyst to each of these just to speed up the reaction. And of course, we've added some soap to it to catch the bubbles. That way, we're able to provide something for those elephants to brush their teeth with. So Julia is going to help me since, let me double check. Yep, I only have 2 arms, not 4. So on the count of 3.
Ready.
All right. 1, 2, 3. There we go. And now the elephants can brush their teeth.
All right, so we hope that you've had a wonderful time tonight, but tonight is just an introduction to chemistry. Over the course of the year, through the Pathways program, which Maria, Allison, and Claudia run, you will have many opportunities to participate in chemistry outreach events. You might be able to learn about a specific area of chemistry. Today you've learnt all about the general principles of chemistry, but you might learn about organic chemistry, which is particularly relevant to synthesizing pharmaceuticals. You might learn about inorganic chemistry, which is more relevant to making plastics or large-scale products. If you were completely scared with what we did tonight, you might want to be a theoretical chemist, and then you can just think about things. Maybe you're interested in how the body works. If you study biochemistry, you will learn about that. And you should look for the Pathways emails to see more details. The garden! Oh.
Hit auto, there's an autofocus button.
Look at that garden.
Now, before we do one last demonstration for you, I've been told that you all entered your names into a raffle. So we are now going to draw that raffle. Matt, could you please pull out a name from here? So Matt has pulled out a name. Before we announce that, I should tell you that the prize is a $100 gift certificate to the Connecticut Science Center. So it's not as cool as what you saw tonight, but it's really pretty fantastic. And you'll notice that we didn't give this gift certificate to Dave to burn. So, our winner of the gift certificate is Fat Manure Ica, and I apologize if I pronounced that wrong, from Bailey Middle School in West Haven. Congratulations. I'm going to give... Okay, so... From all of us, thank you very much for coming tonight. And before you leave, we're going to show you one last demonstration.
Yes. So I've shown you several times when we show you how chemists reveal things, and Matt has made something very special here that will be revealed. Is this the front? Yes. Okay. And you can see it doesn't say anything. What's wrong? We need some chemistry here. Oh my gosh, that's really long. Okay. we need to reveal this, and in order to reveal this, we need the whole team here. And so I'd like you to give one last hand for each of our people, and I'm going to give each of them one of our weapons that we can use to reveal the message on this. Okay, so a big hand for Emily Barth. Woo! Big hand for Julia Curley. Nick Smith. All right, Nick. Dave Charbonneau. And of course, our ringleader and master here, Professor Nilay Hazari. and Matt Espinosa, my partner in crime. All right, let's see it. Go for it.
Oh.
You're trying to.
I need help, guys.
All right. Woo! Thanks for coming, everyone.